So yes, hello everyone. So I'm back here again. Yeah, we have this example from your notes, lecture notes. So calculate the pH of the solution before any base is added. So if you are to calculate the pH of the solution before any base is added, I think it will be wise enough to just start by writing the chemical equation of the acetic acid, which is CH3. We can both agree that this is a reversible reaction. So it will yield H plus CH3, the acetate ion. So this is aqueous, this is aqueous, this is aqueous. Now, for me to find the pH, and I think I need to take note of my Ka. So that means I can easily find the concentration of this, right? And why do I need to do that? I need to do that so that I can simply find the pH of the solution, right? So I can find the concentration of, so what I need right now, I need to find the concentration of this hydrogen ion so that I can use it in my formula, because I know that pH is simply negative log the concentration of H plus, right? So, but then how can I do that? Well, we were given the initial concentration of acetic acid, which is this one, right? And this is a 1:1 ratio. So that means I can find this using the ICE table, right? I can find the concentration of this hydrogen using the ICE table. So maybe let me draw down my ICE table. ICE table. I'll use the concentrations. ICE table, right? So in the ICE table, I think what I need is simply initial, and then change, and then equilibrium, right? Yes. So this is what I need, and then this, yeah, this is what I need. So yeah, so basically this is it. And then this one is for the acetic acid itself, then the H plus ion, then the acetate ion, the acetate, right? So now I need to fill in my table. I need to fill my table. So the initial molarity of the acetic acid, you were given it's simply 1. So I'm going to go ahead and write that and pick a different marker. So it's 1.00, right? And then the initial, since this one the good product in, you know, hurry, this will be 0, this will be 0. But then the change, for the change, that means this will simply be minus x, and this will be plus x, this will be plus x, right? And then at equilibrium, this will simply be 1.00 minus x, and this one will simply be x. This one also will be x. So yeah, so from here, that means I can write my Ka expression, right? And then remember that my Ka expression from the equation that I given you above, Ka will simply be the concentration of our products over right. And we're going to also, this happens at equilibrium, right? So that means at equilibrium you have these concentrations, so I'm just simply going to put my concentrations here into this formula, and then you know that your Ka from this question, your Ka is simply 1.8, right? So that means I can find the concentration of of the hydrogen ion. So that means Ka is simply 1.8 times 10 to the power 15. Right? Everybody can confirm that from the question. Oh, it's negative 5. It's negative 5. It's negative 5. My bad. Is equals to the concentration of this acetate ion and the hydrogen ion at equilibrium is X. It will be X and then multiplied by X. They're both X, so that will give us X squared. And then the concentration of this acetic acid at equilibrium is 1.00 minus X. And then maybe to simplify the right hand side, this will be X squared over 100. No, not 100. It's 1.00 minus X. So yeah, and then from here, you need to find X. Why do you need to find X? Because you know that from the ICE table, this X is the concentration of the hydrogen ion, and it can help you to find the pH, remember. So that means from here, we will take our assumption as usual. We will assume that X is very, 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 very small, right? To a point that 1 minus 1.0 minus X is simply 1.00, right? So this is our assumption. This is how to approach this question. So I won't explain much why we assume. So we have talked about that for the longest time, I think so. So that means if this X is less than this, that means it won't have a significant impact here. So that means X will simply be root of 1.8 times 10 to the power negative 5, right? And then if you press your calculator very well, this will give you 0.00424. And then if this is X, you can also conclude that the concentration of this is simply 0.00424, right? And what did I do here? Maybe I played the first one on you here. No, it's very simple, such that if after assuming that X is very, very small than this one molarity of the acetic acid, it only means that 1 minus X is still just this one, right? So that means you will have 1.8 times 10 to the power negative 5 is equals to X squared divided by 1. And X, any number divided by 1 is just itself, right? So that means X squared is equals to that. And then making X subject the formula, I'm taking root of that. And then hence this. So then also we agreed that the concentration at equilibrium of the H plus ion is X, and then after finding this X, we can also agree that this is the concentration of the H plus. That means I can find the pH by simply saying pH is equals to negative log 0.00424. Then this is simply, if you press your calculator very well, that's 2.37. So yeah, that's it for part A. Yeah, so I don't think for part A, I don't know any way of doing this without using the ICE table. So if you have any another way, please share with us. Because a lot of people, they struggle with the ICE table, and I don't know why. So now, part B. Part B, you're asked to find the pH when half of the acetic acid has been neutralized. So, when half of the acetic acid has been neutralized, so how can we go about this? Well, the pH, so that means when half of the acetic acid is being neutralized, we can both agree that from the equation I gave you above, CH3OOH, the concentration of the acetic acid is equals to the concentration of the acetate ion, right? And why is that? Because from our balanced chem equation, this one above here, this is a 1-to-1, right? This is a 1-to-1. This is a 1-to-1. This is a 1-to-1, right? So that means if you want to find the concentration of this, when you have this, you just use the ratio 1:1, it will give you the same. So that's my conclusion here. That's what I'm talking about here. When I say the concentration of the acetic acid here is equal to the concentration of the acetate ion. So that means if I use my formula pH, this is the Henderson equation, pKa plus log divided by the concentration of the salt itself, CH3, no, the acetate ionic, it's also the salt of this, so CH3 OH. So now, since these guys are equal, it only means this will be 1 here. It means this will be 1, right? Because dividing same things, it just give you 1. So I can conclude that, okay, my pH for this is simply pKa is equals to negative log Ka, right? So if you plug in our numbers, this will be negative log 1.8 times 10 to the power negative 5, and then this will give us 4.74. So that's the answer for part B. Now, how easy was that? Yeah. And then part C. If you go to part C, now find or calculate the pH of the solution at the equivalence point. Now, for the equivalence point, we can simply find a new page. Yes, for the equivalence point, I think you can simply pick a black marker. So, for the equivalence point, I think we can just start by calculate the volume of the sodium hydroxide needed to reach the equivalence point. Like step number 1, we need to find the volume, right, of sodium hydroxide, right, needed to reach the equivalence point. Now, how can you find that? Now, remember that the moles of the acetic acid here, you can find them. Maybe there is a question. Okay, moles of CH3OH, right? This, how can we find this? We want to find the volume of this. So we can start by finding the moles of the acetic acid. So how can we do that? We can simply multiply by 0.55 liters times 1.00 ml, and this will give you 0.0500 moles of this CH3COOH. Yeah, and then after that, at the equivalence point, it only means that the moles now at equivalence point. This is the at equivalence point. The moles of sodium hydroxide is equals to the moles of CH3COOH. Now you need to get this straight. If you don't get this part, you may never arrive at the answer, because there's no other way you can find the volume of sodium hydroxide without knowing the moles. So that's why you have to agree that at equivalence point, the moles of sodium hydroxide simply equals the moles of the acetic acid, right? And then that means we can now find the volume of sodium hydroxide. So finding the volume of sodium hydroxide that we didn't know is simply 0.0500 divided by, and we're given this molarity from the question, that's mole, and this will give you 0.0625 liters. So maybe to convert it to ml, it will simply be 62.5 ml. Yeah, so now maybe you can find the total volume. So the total volume of the equivalence point is so now maybe let's find the total point. pardon, the total volume at the equivalence point. So to find the total volume at the equivalence point, we simply need to add this and the 50 ml that we had already. So that will be 50.0 ml plus 62.5 ml. Then if you press your calculator very well, this will give you 112.5 ml. Then maybe back to liters, this will be 0.1125 liters. So now, after finding the total volume of the total volume at the equivalence point, I think you can go ahead and find the equivalence. So okay, now, no, pardon me. So at equivalence point, one thing that I forgot. Now at equivalent point, all the acetic acid has been converted to acetate ion. We have to agree on that. Now, if all the acetic acid has been converted to the acetate ion, so that means the concentration of the acetate ion, right? I can find it by simply dividing the moles over the total volume, right? This will give me 0.444, right? And then and also another thing, at equivalence point, all the acetic acid has been converted to the acetate ion, right? That means if this is a 1-to-1 ratio, we can simply find the concentration of the acetate ion by simply dividing the moles of the acetic acid divided by the volume at the equivalence point. And also this acetate ion, we know that it will hydrolyze in water, right? And if it hydrolyzes in water, you know that this is CH3 plus H2. Or to hydrolyze, it means it produces a hydroxide ion. Yeah. This will give you CH3COH plus the hydroxide ion. Then we know this is aqueous, and this is aqueous, and then this is water and liquid. So now we know that if this hydrolyzes in water, we can simply write and conclude that Kb is equals to Kw over Ke, right? And we know Kw is simply 1.0 times 10 to the power negative 14 over Ka. We're given Ka times 10 to the power negative 5, and this will give you 5.56 times 10 to the power negative 10. Yeah. Now, why do I need to find Kb? I need to find Kb so that I can use my ICE table, right? To find, well, I want to use my ICE table to find the concentration of this hydroxide ion, so that I use it to find the pOH, and then I can subtract the pOH from pH from 14 to find the pH. So if I have my Kb, so this is my Kb, right? So that means I can write an ICE table, right, for this equation here. And also I know that I have the concentration of this, right? And that's all what I need. So now, let me find a new page. Oh, page is finished. Or let me just wipe my board up here. Give me a minute. Let me wipe my board. How did this happen? Okay, or maybe I can use this one. Yeah, let me try and wipe my board here. So this, we don't need this, we don't need this, we don't need that, we don't need that, and that. So, and then we also don't need that. We'll see about that. Then maybe this one also. We don't need this, we don't need this, need that. We don't need that. We don't need that. I'll try and manage my space next time. So yeah, like I was saying, I need to write down the IC table, right? For when the acetate ion hydrolyzes in water. So let me write it here. So that means here is the acetate ion itself, then acetic acid, then the hydroxide. Yeah, so that's it. So the initial, we can both agree that we just calculated this to be 0.44, and then we know this will be 0, and this will be 0, then this will be minus x, this will be plus x, this will be plus x also, and then at what happens in kilogram? We know this is just x, and then this is 0.44 minus x, right? So now, that means I can use these concentrations at equilibrium to find the concentration of the hydroxide ion, right? So that means I can simply write Kb, my Kb is simply, oh no, my Kb, let me wipe this down. I don't know why it's misbehaving. So that means to write my Kb, I can simply say this is CH3OH, concentration of OH over the concentration of reactant, which is just the acetate ion in this case, right? So and then I know that we just calculated our Kb. It was simply 5.56 already. Now notice something here. This is something that's similar that we wrote. So maybe I can replace the concentrations with x and home. So then, excuse me, so that means will be, you know, the concentration of the acetic acid and the hydroxide ion is x. So it will be x times x up there. So that will be x squared. And then here will be 0.444 minus x, right? And then we know that the Kb is simply, no, pick a different marker. Simply, this Kb was simply 5.56 times 10 to the power negative 10, right? Now, we are going to take our assumption again, right? So if we take our assumption, so let me just clear this. This one, I'm going to need it, and this one also. This question was not supposed to take 30 minutes. It's just that my body is misbehaving. Yes. Now, continuing. Like I said, whenever you arrive here, we are going to take our assumption, right? Let's assume that this x is very, very, very small from this 0.444 to a point whereby if we subtract this x from 0.44, we still get 0.444 approximately, right? So that means I can easily conclude and say 5.56 times 10, that's the Kb, is simply equals to x squared over 0.444, right? Now, if you look at this, from here, I have this equation. Now I need to find x. So how can I find x? I can multiply by 0.44 both sides, right? And then divide by, then, no, after multiplying, then I take the square root of that. So if I multiply by this, so we can both agree that x is simply the square root of 5.56 times 10 to the power negative 10 multiplied by 0.444, right? We can both agree that. And then we found out that this x is simply, so if you press your calculator very well, you'll find that x is equals to 1.57 times 10 to the power negative 5. So, and then also from our ICE table, we are both agreed that the concentration of this hydroxide ion is equals to x, which is equals to this, which is equals to this. So now we can find pOH. So that means we can find our pOH, right? From our formula, we know that we both know that pOH is equals to negative log OH. Then if you slot in this concentration into this formula, you find out that the pOH is equals to 5.80, right? And then we know that pH is equals to 14 minus pOH, right? And then if you subtract, so if you're going to subtract this 4.8 from 14 to find the pH, so we can conclude that the pH is equals to 9.2. So basically that's it with this example. So I hope this helps you. You should expect this type of questions in section B of your Chem 101 exam. So familiarize yourself with the ICE table and this type of questions. If you have any question, please talk to me. Thank you.